Welcome to the video on chemical reactions. One type of reaction is called a single replacement reaction. This is where we have one compound that comes in that has two species together, and it combines with a compound that is on its own. And in our products, the compound that was on its own is now combined with something, and a different thing is on its own. So this is called single replacement. Double replacement is when we have two compounds come in, and they both have two species. In our product, they just switch. So the copper here gets together with the nitrate here to become copper nitrate, and the chlorine and the silver are left over to make silver chloride. That's called a double replacement reaction. Composition reaction is when we actually combine two things together. So two things come in alone and then they leave together. And a decomposition reaction is the opposite, where we have a compound that breaks up into smaller pieces, and that's called decomposition. So there are three primary types of chemical reactions that we're going to talk about in this class. And the first is precipitation reaction. Precipitation reaction involves compounds being placed in water, and if they're soluble, they dissolve and they go right into the water. And if they're not soluble, they do not dissolve, and so they stay as solid in the water. The word precipitate is a solid that falls out of solution in a precipitation reaction. One example is lead iodide. When we have lead ions that come together with iodide ions, the lead gets together with the iodine in a PbI2 ratio, and that is solid. The way that we know that that is solid is we look at the solubility tables on the back of our periodic table. And here are those tables that I was just referring to. Note that the top table on your periodic table talks about compounds that are soluble, except the ones that are here. So these are the exceptions. So the ones here highlighted in yellow are insoluble. In contrast to that, the bottom table on your periodic table, or the one that's indicated right here, these are all insoluble, except, so if we talk about group 1 and ammonia with all of these, and or group 1, calcium, barium, strontium, and ammonia with sulfides and hydroxides. These things in purple are now soluble. Everything else is insoluble. So keep those two things straight. And when we're writing precipitation reactions, we are going to have to write the phase. And aqueous, AQ, means that it is soluble. So we put lead nitrate together with sodium iodide in solution, and we end up with lead iodide. That's the solid. That's the thing that precipitates out. And then sodium nitrate is aqueous as well. If when you do the chemical reaction and you start off with these two aqueous things, you switch the partners and you end up with both things being soluble, both things being aqueous, we are going to use the term no reaction to describe that. The second type of reaction that I want to talk about today is called an acid-base reaction or a neutralization reaction. In each case, we are going to have an acid come together with a base, and the products of these reactions are always going to be water and salt. The base, by definition, brings in an OH to our reaction, and the acid, by definition, brings in an H to the reaction, so that H and OH get together to form liquid water. So we're going to have water as one of our products, and it comes from the H from the acid and the OH from the base. What's left is the Na of the base and the Cl of the acid, and that gets together. Whenever we write our salt, we need to make sure we write it with the cation first and then the anion. So we write our salt, make sure we do the crisscross and make sure it comes together in the right ratio, but that is our salt, NaCl, and we're going to add aqueous after that. The hydronium ion is actually protonated water, so it's H3O+, just for your reference. We can have an acid that is aqueous and a base that is a solid, and they will still react. We do not need both of these reactants to be aqueous in order for this reaction to happen. And the last type of reaction that I would like to talk about today are redox reactions. These are reactions that have an oxidation reduction happening. And in this case, what happens is we have a transfer of electrons. Oxidation is when we have a loss of electrons or an increase in the oxidation number. Alternatively, reduction is when we have a gain of electrons and we have a decrease in the oxidation number. And I will show you how to calculate the oxidation number. One way that people remember this trend is oil rig. Oxidation is losing and reduction is gaining. Or Leo the lion says grr. So losing electrons is oxidation, gaining electrons is reduction. And this is just a little side note. If you have a compound that is doing the oxidation, itself gets reduced, but it is causing the oxidation, that is called an oxidizing agent. I just wanted to say that every time you have an oxidation, you have to have a reduction, and there can't be any gain or loss of electrons overall. So every time there's an oxidation, there's a subsequent reduction. And if you have a compound that is actually becoming oxidized and it is forcing the reduction of something else, that is called a reducing agent. So the oxidation number is often the same as the charge. Oxidation numbers are going to be required in order for us to calculate redox reactions. So the oxidation number is a number assigned to the atom to keep track of the number of electrons. Here are some rules in our table over here. The oxidation number of an atom that's in its elemental form is 0. The oxidation number of a monoatomic ion is the same as its charge. The oxidation number of group 1A metals in a compound is always +1. The oxidation of group 2 metals is always +2. The oxidation numbers of fluorine in its compound is always -1. And the oxidation number of hydrogen is +1 if it's in a nonmetal compound and -1 if it's combining with metals, and that is called a hydride. The oxidation number of oxygen in its covalent compound is usually -2. Exceptions include peroxides, H2O2, in which the oxygen is -1. In binary compounds containing group 7 elements, typically have an oxidation number of -1, and group 6 elements typically have the oxidation number of -2. Group 5 elements have an oxidation number of -3. The sum of the oxidation numbers of all atoms in a molecule or ion must equal the total net charge of 0. So if we practice a few here, iodine is always -1, and there's 2 of those, so lead is going to be +2. Calcium oxide. Oxygen is always -2, and calcium is always +2, so that goes together nicely. Carbon dioxide. Oxygen is always -2, and there's 2 of those, so carbon is going to be +4 here. Oxygen and its diatomic, right? That's just going to be 0. And so let's plan on working on the rest of these in class, but that'll help us know redox reactions if we can establish these oxidation numbers. So in using this reaction here as our first example, let's figure out the oxidation states of NO2. So we're going to look at each individual atom. The nitrogen is next to 2 oxygens. Each oxygen is -2, and so there's 2 of those, and so it makes the nitrogen +4. Hydrogen here is by itself, so that's going to have an oxidation state of 0. And over here in the products, in ammonia, the hydrogens are each going to be +1, and there's 3 of those, so it makes our nitrogen -3. And in water, oxygen is -2, so that makes each of our hydrogens +1. And so if we look at this reaction, we see that nitrogen goes from +4 to -3. Nitrogen goes from +4 to -3. And our hydrogen goes from 0 to +1. And it goes from 0 to +1 in both cases. So our hydrogen goes from 0 to +1. So remember the definition of oxidation is increase in oxidation number. And in this case, our hydrogen is being oxidized because it goes from 0 to +1. And the definition of being reduced is a decrease in oxidation number. +4 to -3 is a decrease. So the nitrogen is being reduced. So you can also just indicate it here. Nitrogen is being reduced and hydrogen is being oxidized. And then, of course, if nitrogen is being reduced, then it becomes our oxidizing agent. And if hydrogen is being oxidized, it becomes our reducing agent. And that's how you would solve a redox equation. You determine the oxidation numbers for each atom. You determine which oxidation number goes up, that's oxidation. Which oxidation number goes down, that's reduction. Label it, and then determine your oxidizing agent and your reducing agent. And just one last thing on this slide, when you have redox reactions involving oxygen, we can do that 2 types. One is combustion, which is basically burning. We combine our compound with oxygen and we get carbon dioxide and water as products. That's combustion. Or corrosion. and corrosion typically involves a metal. So we're going to have to often interpret and write the formula. Then we're going to have to do the crisscross and make sure we put everything together in the right ratios. And then we're going to have to balance the equation and make sure that we have the right number on both sides. And then once we do all of that, we have to determine the phases of the compounds, for example, aqueous, liquid, solid, gas. Then once we are done with all of that, balanced phases, everything's put together correctly and everything's named correctly, then we can talk about writing the molecular equation. The molecular equation contains everything as written. It's the full reaction. We have all the reactants plus all of the products as given in the problem. The next step is to write a complete ionic equation. And for ionic equations, anything that says aqueous breaks apart into the ions. Anything that is liquid, solid, or gas stays intact. So if we have HCl, if we break these ions up, the H becomes H plus aqueous, the Cl becomes Cl minus aqueous, the Na becomes Na plus aqueous, OH becomes OH minus aqueous, and over here Na plus aqueous, and then we have Cl aqueous and Cl minus aqueous. And because the H2O is liquid, that stays together and we end up with H2O. So that is the complete ionic equation. Complete ionic equation is anything that is aqueous completely dissociates and we write the ion. Anything that is solid, liquid, or gas, we write it as a compound. Now, the next step is my favorite part. We have to get rid of all of the spectator ions. So a spectator ion is an ion that just hangs out in the reaction and does not actually participate in any way. So for example, Na exists as a +1 ion on both sides. So Na is not involved in the reaction, and that is a spectator ion. Cl minus is not involved in the reaction. Cl minus exists on both sides. So that also gets crossed off. And so what we have left is H plus aqueous plus OH minus aqueous gives us water liquid. And so that now becomes our net ionic equation. It's all of the things left from the complete ionic equation after you cancel out the spectator ions. And a net ionic equation is a simplified equation that results in the removal of the spectator ions. So we have the molecular equation, which is the full equation before anything happens. The complete ionic, which breaks all the aqueous things up into their individual ions, and the net ionic, which involves getting rid of all of the spectator ions and having a simplified equation. Another way you can look at the net ionic is we have H2O formed as a liquid. So that's our chemical reaction. And so we're going to need to make sure that we include the ions that needed to be brought together to make water. So OH minus and H plus. So the procedure for writing ionic and net ionic equations, switch the ionic partners in the reactants, always pair a positive with a negative, and always put the positive first. Fix formulas for the new products using subscripts, so you have to do the crisscross. Balance the equation, so you want to make sure you have the same amount on both sides of the arrow. Check the solubilities of the reactants in the products and put in parentheses solid, liquid, gas, or aqueous in the molecular equation. And then to get the complete ionic, we have to write all the compounds as dissociated ions unless they are insoluble, solid, liquid, or gas. And then to get the net ionic, you cross off the spectator ions. So if we work on this problem right here, lead, we know that nitrate is -1, so, and there's 2 of those, so lead is going to have to be +2, nitrate is -1. So when we put lead together with iodine, if lead is +2 and iodine is -1, we see we do that crisscross, so we get PbI2. Na is +1, iodine is -1, Na is +1, nitrate is -1. And so the rest of those combine at 1 to 1. So when we balance the equation, we're going to include the coefficient of 2 here and the coefficient of 2 here. So now we've balanced the equation. We have our subscripts and superscripts right. So now we have to put our phases in. And if we're going to put our phases in, we're going to use the solubility table. This is soluble, so it's aqueous. This is also soluble, so it's aqueous. This is not soluble, so that's solid. And this is soluble, so it's aqueous. So the solid that we have to think about is lead, iodide. That's the complete molecular formula. We have all of the compounds crisscrossed correctly, so they're put together in the right ratios. We have balanced chemical equations, so we've added coefficients to make sure everything's good, and we've added our phases. For the complete ionic, we're just going to break everything apart. So we have lead plus 2, nitrate minus 1, and there's 2 of those. So remember, in the complete ionic, we're going to have to carry down the coefficients. We have 2 sodiums and 2 iodines. And then in our products, we have lead iodide, which is a solid. And so we know that is going to come into play for our net ionic. And then we have sodium plus, there's 2 of those, and nitrate 1 minus, there's 2 of those. And so if we now cancel out all of our spectator ions, lead is not an ion on both sides, so that one we're going to keep. NO2, there's 2 of them on both sides, so that's a spectator ion. Sodium, there's 2 on both sides, so that's a spectator ion. Iodine is not an ion on the product side, so that's going to also be part of my net ionic equation. So if I write my net ionic, I have lead 2 plus aqueous, iodine 1 minus aqueous, gives me lead iodide solid. And so that is my final net ionic equation. There are a couple pages of practice problems. If you want to get started, you can. Otherwise, we'll plan on doing that in class. Okay, there you go. Chemical reaction.